So the chemical shift you will identify from the peak. Like example, you have propanol. Another molecule, propanol, is there. So what? How? First thing, how many hydrogen environments are there? There is CH3, there is CH2, and there is OH. So three hydrogen environment. So three hydrogen environment. First hydrogen environment having. So if I say this is hydrogen environment A, B, and C. So hydrogen environment A is having three hydrogen, B is having two hydrogens, and C is having one. So in low resolution, like one should be 3 centimeter, then other should be 2 centimeter and 1 centimeter. But what about their chemical shifts? So CH3 is next to CH2. So if CH3 next to carbon chain is there, that's from 0.7 to 1.2. So you can see from 0.7 to 1.2 in that range is there. Then for CH2, for which the next is C double bonded with O. So CH2 or CH with next to that is C double bonded with O. It's from 2.1 to 2.6. So this one is from 2.1 to 2.6. So that's why it's from 2.1 to 2.6. And then OH group is there for carboxylic acid. Sorry, this is propanoic acid. I had said propanol. Uh, so C double bonded with O and OH. So C double bonded with O and OH. The peak is from 10 to 12. So from 10 to 12, you can draw anywhere. First thing you recognize, like I will get a chemical shift for environment A around like 0.7 to 1.2. I can draw anywhere. Example, I will draw at 1. Then for B, it will be from 2.1 to 2.6. Example, I will draw at 2.3. It's up to you where you want to draw. And for C, it is from 10 to 12, so I can draw it around 11, or it means in this range I can draw. Now, so in low resolution, if I draw a low resolution NMR for this propanoic acid, so a chemical shift 0 means the tetramethyl silane TMS will be there. Then 1, 2, 3, 4, and 12. So this is a chemical shift. And the relative intensity there is there. If I draw a low resolution NMR, so for A, the environment A, where I will get at 1, so and that is the height should be 3 centimeter, like the intensity should be 3 times compared to others. So this will be 3 centimeter example. Then another I will get at 2.3. So 2.3 somewhat here, so that should be 2 centimeter. And the other one is around 11 I will draw, but that will be 1 centimeter. This is low resolution NMR. But in high resolution, what happens? These peaks will further split. Like the number of the peaks remain same, but that peak will further split, and it will split into n plus 1 according to the neighbor. So for A, environment A, because the neighbors are 2 hydrogen, so how many it will split further into? It will split into triplet. For B, the 3 hydrogen environments are 3 hydrogen are there in the neighbor, so it will split into quartet. And for this one, 0 hydro environment, so it will split into singlet. So means I'll get a triplet, like this will be triplet. And how, what is a triplet? Triplet is 1 3 1. Like I will draw 3 peaks, but when I draw the relative intensity around the same chemical shape, but when I draw them, I'll draw triplet. So triplet, it is 1 3 1, and I have to draw around 1, so it will be like example 1. This is triplet. Then I will, for B, I will get a quartet. Quartet means like this peak divided into 4. And what is a quartet? In a quartet, it is 1 3 3 1. So this whole peak will divide into 1 3 3 1. and that was at a chemical shift of 2.3. So around 2.3, I will draw 1, 3, like comparison with them, within them, the peak, 1, 3, 3, 1. And then I'll get a singlet which is having one hydrogen. So around 11, I will draw a singlet. That's it. So this is NMR, nuclear magnetic resonance, high resolution NMR for propanoic acid. Is it clear? Is it clear, the NMR for propanoic acid? So example, here it is ethyl ethanoate. So in case of ethyl ethanoate, first you identify. Yeah, in the previous example, the intensity of A and B should be different because they have different hydrogen in environment, like different hydrogen number of hydrogen in each environment. A was having 3 hydrogen, B was having 2 hydrogens. Like another example, if you have ethyl ethanoate, so in case of ethyl ethanoate, you have CH3, then C double bonded with O, CH2, and then CH3. So you can see 3 hydrogen. Why 3? Because this CH3 is totally different from other. The neighbor is carbon, and this one neighbor is CH2. So 3 hydro environments are there, and it's up to you. Like example, if I'm saying this is hydro environment A, this one is hydro environment B, and hydro environment C. So what is the relative intensity? It will be 3 is to 2 is to 3. That is in low resolution NMR, like one should be 3 times compared to the other. Now, what are the positions? So for position, you have to go through the data booklet and check. For example, for group A, it is next to C double bonded with O. So neighbor does not have any hydrogen. If neighbor does not have any hydrogen, it will be a singlet. And what about the chemical shift? At which position we'll have a chemical shift from 2.1 to 2.6? Why? Because this is attached to C double bonded with O. So when it is attached to C double bonded with O, you can see the range is from 2.1 to 2.6. So it will be a singlet at 2.1 to 2.6. So you can see there's a singlet. Then for environment B, the neighbor are 3. So if neighbor are 3, it will split into 4. So it will be quartet. And what about the region? The quartet in which region? Because next to that, the group B, it is next to, like it is C double bonded with O and carbon is there. So where we get a chemical shift for C double bonded with O? So you can see for C double bonded with O and O, if carbon chain is attached, that's from 3.7 to 4. So that's why we will get a peak at 3.7 to 4. And for the last, this CH3, because next to this is a carbon chain, like CH2 is there. So if CH3 next to its alkyl group, then it is from 0.7 to 1.2. So 0.7 to 1.2. And the splitting, what will the splitting? Because next to this are 2, so it will split into triplet. So C is splitting into triplet, you can see, and triplet will be 1, 3, 1. A is a singlet because neighbor is 0 hydrogen. And what about B? B is quartet because the neighbor having 3 hydrogen. Is it clear? The low this high resolution NMR. If it was a low resolution NMR, then what we will do? Only thing the difference will be like what are the number of hydrogen, that will be the relative intensity. That's it. Like this is having three hydrogens. Environment A. Where is A? This one is A at chemical shift. This one is B, and this one is C. So 1, 2, 3, 2, and 3. So for A, we will get from 2.1 to 2.6. So from 2.1 to 2.6, we'll get A. For example, 3 centimeter. Then for B, from 3.7 to 4.1, from 3.7 to 4.1. And it's like the two hydrogen, so this will be example 2 centimeter. And then for C, it's zero point 0.7 to 1.2. So zero point 0.7 to 1.2, and also having three hydrogen. So that will also have three hydrogen. That's it. This will be low resolution NMR. But high resolution, these peaks further split into singlet, triplet, and quartet according to their neighbors. Is it clear? This example of high and low resolution NMR. Then infrared spectroscopy. Basically, what is infrared spectroscopy? As the bonds are polar, the bonds tend to absorb the infrared radiation. So using the absorption, the wave number, like how many waves are absorbed per centimeter, we can identify the type of the bond. The below 1500 is known as a fingerprint region, because every compound is having a unique spectrum. So using this, we can recognize the whole compound. But normally, we have to identify the type of the bond. So how we can identify the type of the bond? These are the ranges given. Like if CO bond is there, it will absorb from 1000 to 1300. C double bonded with O 1640 to 1750. CH, OH, NH, and OH of phenol and alcohol, this range. So example, you have a spectral of a infrared spectra of butanol. So in this CH3 is there, CH2, CH2, C double bonded with O, and H is there. So this C double bonded with O, it will absorb from 1600 to 1750. So this absorption peak, we can identify the type of the bond present. Same way, some of them are weak absorption, some of them are strong absorption, some are having a wide range. So example, OH absorption tend to be broad. You can see the peak is broad peak as compared to the others are sharp peaks. So if we have C double bonded with O and OH, so C double bonded with O and OH is there. So OH of alcohol and phenol and OH of carboxylic. So broad, this will be very broad peak for 2500, 3300. So we identify this is because of OH, and C double bonded with O, that's from 1640 to 1750. So using this, we identify like OH is also there for carboxylic and C double bonded with O. So basically, this is a carboxylic group present in this molecule. So using this infrared spectroscopy, we can identify the type of the bond present. Uh, this infrared spectroscopy we already discussed in AS chemistry, so I expect you can also do examples and go through the previous examples in AS chemistry. Then Mass spectrometer, it is used to find the relative molecular mass of a compound. Basically, what are the stages involved? First, we vaporize the sample, then ionize, then accelerate and deflect, and detection is done. So, the highest mass to charge ratio peak is known as the molecular ion peak, and the one which is highest intensity is known as the base peak. So, what happened, like example, if you have this one is butane, so CH3, CH2, CH2, CH3. So what are the splittings? Because it will break into a positive ion because electron is removed, and radical. Radical cannot be detected or accelerated because there is no charge. Only the ions can be accelerated, the positive ion. So first, when we knock out the electron, the whole molecule get a positive. But as this molecule is moving, it can disintegrate into fragments. So you have to make the possible fragment. Like what could be the possible fragment? If it is breaking start from the left hand side, so you may have CH3, so you will get a peak at 15, or it will be CH3, CH2. So CH3, CH2, 24 plus 5, you'll get a peak at 29, or it might split into CH3, CH2, CH2, 49, 29 plus 14, 43, or you will get the whole molecule, which is 58. So if we break from left hand side, the peaks we will get at 15, 29, 43, 58. Or if we break from the right hand side, it will be identical because the molecule is identical, like CH3 will be there, that's 15, or CH3, CH2 will be there, or CH3, CH2, CH2, or it might break into CH3, CH2, CH2, and CH3. So the peaks, this will be 15, 29, 43, and 58. So basically, identical peaks are there. So you will get peak around at 15, you'll get peak at 29, 43, and 58. So that shows how many fragments you are detecting. Then the one which are highest percentage abundance, that shows that most of the fragment are this type, or most of the molecule dissociate into this pattern. And the highest mass to charge ratio is known as the molecular ion peak. And that's a whole thing which just now I discussed with you. This was about, the first one is about butane, the second one is of butanol. So for butanol, what are, because butanol, so this is butanol, CH3, CH2. So this will be 15, 14. This will be carbon, 12 plus 16, 28. And then 15 will be there. So what are the fragments it can break? We are getting at peak at 29. So why 29? Basically 29 is due to 15 plus 14. We are getting a peak at 43, and this is the highest one. So why it is 53? Because 28 plus, sorry, 43, 28 plus 15, that's 43. So that's the highest. It shows most of them dissociate into this. We are also getting a peak at 57. So 15 plus 14, 29, 29 plus 28. So we'll get at 57. And the last one, 72. So 72 means it's the highest peak. So that's the highest mass to charge ratio peak. The highest value of mass to charge, that's known as a molecular ion peak. So you may have a mass spectrum, and you have to identify like what are the fragments responsible for the certain peaks. Is it clear? The mass spectrum. Then we can use a chromatography. A chromatography, you took paper chromatography. Basically, in a chromatography, you have two phases. One is called a mobile phase. The phase which is moving is known as the mobile phase. Another one is a stationary phase. Like in a paper chromatography, what we used to do, we draw origin with a pencil, then we place a substance which we want to identify or separate on the origin, then dip this inside a container which is filled with a solvent. As the paper absorbs this solvent, the solvent will rise, and with the solvent, the component, like example, if it was a mixture of two, so then it will rise with the solvent. So what is the stationary phase? Stationary phase is a paper. And what is the mobile phase here? Mobile phase is a solvent. So the attraction between the, because there is an attraction between the stationary phase and the particles of the substance which we are separating, and there's an attraction between the stationary phase and the particle, the substance which we are separating. So if the attraction between the mobile phase and the substance which we are separating is more, it will rise to a greater height. If the attraction between the paper, like the stationary phase, and the substance which we are separating is more, then it will rise to a lower height or it will not rise. So using this technique, we can identify or we can separate the two substances. That's the main technique, paper chromatography. So the chromatography can be paper chromatography, it can be column chromatography, it can be gas chromatography as well. So paper chromatography already we are done, like we discussed. The column chromatography. So in column chromatography, what we do, separated by depends on the balance between the solubility of moving phase and the retention in the stationary phase. Means you can see the column chromatography also. Like this is a column chromatography. So what happened? First, what we have, a column containing a stationary phase. So there are fine particles are there, a solid particles um, known as a stationary phase, suspended. Then we load the sample which we want to separate. When we run down the sample, well, like open the tap, so sample will come out. So the component which are present in a loaded sample are also separated from each other. So red, green, and blue. Which one is having a greater attraction towards the stationary phase? Red, blue, or green? Which one is having a greater attraction to the stationary phase? So blue is having a greater attraction because blue does not move quickly. Red move quickly, it means red is having greater, as we tap out this solvent, so it's having a greater attraction to the mobile phase, so it will come out first. Then we have the green, which is moderate attraction, and then we have blue, which is having greater attraction towards the stationary phase. So this is the main technique, which is also known as a column chromatography. So separating by a column chromatography, separation by a column chromatography depends on the solubility in the moving phase and the retention in the or attraction in the stationary phase. Then we can also use, we can have high performance liquid chromatography as well. So in high performance, only the different, like there is a high performance liquid chromatography, what we have, We have a stationary phase such as silica gel is a stationary phase, and the mobile phase is a liquid. We can also use a gas liquid chromatography to separate the mixture of volatile liquids. Volatile liquid means the liquid which can easily be vaporized. So what happened? First, we have a carrier gas. What carrier gas we use? Normally a gas which is inert, such as group 8 elements. So we can use that as a carrier gas. The sample is injected, and this sample will pass, the carrier gas will pass, so it will pass through the column. On this column, we may have a liquid. So in a gas liquid chromatography, the mobile phase is a gas which is normally inert, helium is there. And stationary phase is a high boiling point liquid absorbed on the solid. Like on this column, there is a liquid present which is on the surface of this solid. So as the carrier gas is taking the sample, so like if it is a sample is a mixture of say two substances A and B. So as A and B will flow with the carrier gas, they will experience attraction toward the stationary phase. If attraction of A is more than the B, so first we will collect B and then we will collect A. And the time interval between collection of one sample to the other, that is known as the retention time. So mobile phase is a stationary gas, is an inert gas such as nitrogen, helium, argon, and stationary phase is a liquid which is on inert solid. Is it clear this technique? Like we take this carrier gas flow, take the sample. The sample may be example a mixture of three substances A, B, C. If A is having more attraction, so A will move slowly through this. B will have greater attraction to the mobile phase, so it will move faster. C also moves slower. So first, if B is attracted more towards the mobile phase, so first we'll collect B, and then example C, and then A. The intensity of these peaks shows how much they are present in the sample, and the difference between them is known as the retention time, the time interval for collecting the two phases. Is it clear, this explanation of the gas liquid chromatography? So if we bring all the techniques together, how we can use all these techniques together to work out the structure of a molecule? So example, using a mass spectrometer. First, we work out the empirical formula. How to work out empirical formula? We can find how much like burn most for this hydrocarbon. We can burn them. So combustion, how much carbon dioxide is produced and how much hydrogen is, water is produced. We can identify the percentage of each element in the compound. So like example, 66.63% carbon is there, 11.18% hydrogen is there, and 22.19% oxygen is there. So first we work out the empirical formula. How to work out empirical formula? By dividing by atomic mass. So we take a simplest ratio. So C4H8 and O1. So using this, we worked out the empirical formula. After working out the empirical formula, which is C4H8 and O. We will find the molecular mass. How to find a molecular mass? Using a mass spectrum. The highest mass to charge value, that's a molecular mass. Empirical mass is 72, molecular mass is 144. So when we divide, we will get 2. That's N. And how to get a molecular formula? So molecular formula is empirical formula multiplied by N. So empirical formula was C4, H8 and O, and empirical formula N is 2. So when we multiply, we'll get C8, H16 and O2. So that's a molecular formula of the compound. Then after molecular formula, we can carry out infrared spectroscopy and identify the type of the bonds which are present. So we are getting a peak. So this peak is suggesting CH is there, and this is C double bonded with O. So it could be because it is C8, H16 and O2. So it can be an ester, it can be carboxylic, it can be a combination of alcohol or carbonyl. But when we look at the infrared spectrum for C double bonded with OH, we found for C double bonded with O, but there is no OH absorption. So it cannot be carboxylic because there is no OH, so it will be ester. Now, as it is an ester, when we worked out the NMR, nuclear magnetic resonance, for this compound, which is having a molecular formula of C4, C8, H16 and O2. So C8, H16 and O2. So how many peaks we are getting? 1, 2, 3 and 4. If we are getting 4 peaks, it means there are 4 hydrogen environment. So we have to arrange this C8, H16 and O2 so that we have 4 hydrogen environment. So when I arrange in this manner, like CH3, then CH2, C double bonded with O, O, CH2 and CH3. If I arrange the structure in another manner, I will not get 4 hydrogen environment. It will be different. So this CH3, this is one hydrogen environment A, B, C and D. Why this CH2 and this CH2 are different? Because their neighbors are different. And why this D CH3 is different from the first one? Because the neighbor is also different. And you can work out from the chemical shift as well. Like one peak, you are getting around 0.7 to 1. That's because of CH3. Another peak, you are getting a chemical shift at for CH3. Next to that is CH2. You are getting around 1.2. Then you are getting a chemical shift with C double bonded with O. Like when C double bonded with O attached to the carbon, the CH2 is there. You're getting a chemical shift at 2.1. And when O and C is there, next to that is CH2, you will get a chemical shift at 4. So when we worked out all together, like this is a valid structure of the molecule. And you can see the chemical shifts. So when C double bonded with O and CH, that's chemical shift 3.7 to 4.1. When C double bonded with O and CH, it's from 2.1 to 2.6. When CH3 is there, it's 0.7 to 1.2. And there's another one. So both of them, like this is also CH3 next to that carbon. This is also CH3 next to that is CH2. That's about 1.2, and the other one is also from 0.7 to 1.2, which is about 0.9. So 4 hydrogen environments are there. This is environment A, environment B, environment C, and environment D. And then how many this environment A will split? Because neighbor 2, so it will split into 3. Like this CH3 neighbors, sorry, for this CH3, the neighbor is 0, then it will split into 1, singlet. For this CH2, neighbor also 0, so this will also be singlet. For CH2 neighbor 3, so it will be quartet. For this CH3 neighbor 2, so it will be triplet. Is it clear? So you have to work all together and work out the structure. So using first percentage composition, we identify empirical formula. Using the mass spectrometer, we got the molecular mass. Using a molecular mass, we got the molecular formula. Using infrared spectroscopy, we worked out what could be the possible bonds. And using those bonds, we identify, using NMR, we identify how many hydrogen environments, and if we work out all together, we can suggest the possible structure of this molecule. So these type of questions are common. Is it clear, this one? Any doubt? So for the unit 4, go through unit 4 and send your doubts. Like if you have many doubts, I will discuss in a class, arrange a class. So we are done with unit 4. The practice question I already shared with you. I'll send again on the group. So I'll end the session and share the recording with you.